All right, so in this lecture, we're going to be picking up where we left off last time in chapter 14. We had just finished our discussion with the association of water and figuring out if you had a certain amount of hydronium present, how much hydroxide you have present, or vice versa. So one of the things that's very important that we commonly use, and you've probably heard just in general conversation about something about pH scale. The pH scale is what we use to characterize the acidity or basicity of a solution. And so the pH scale, it's important to note, is something that is on a logarithmic scale. And when we say logarithmic scale, we sort of mean that the most important part of this property is the magnitude of the property. Is it 10 to the 5? Is it 10 to the 6, 10 to the 8th? Something to that extent. So that's what we're most interested in, is the order of magnitude, and logarithms help us with that, okay? And so we're going to be quantitatively expressing the acidity or basicity of a solution using this pH scale. That pH scale, where it gets that name for pH, it roughly translates to something around the power of hydrogen, okay? And if we look at the quantitative relationship between there, we have the hydronium ions concentration is equal to 10 to the minus pH. Now, if we wish to rearrange that, we have to take the log of both sides. So this would be a log base 10, an log, and not one of those ln's. And we'd end up with the log of the hydronium concentration equals minus pH. We usually rearrange this one more step, moving that negative to the other side. That leaves us with the pH equals the negative log of the hydronium concentration. And so if we are looking at a solution and it's characterized by a pH that is greater than 7, then what we're saying is that we're dealing with a basic solution. So you can see stuff like baking soda or milk of magnesia, ammonia, sodium hydroxide, all of those sit on the top of that scale to the left and are all basic. If we're dealing with something that's neutral, then it should be something that is very close to or at 7. So you see milk, water, and human blood are all very close to a pH of 7. Now, if we go ahead and look on the acidic side where we have the pH is less than 7, then we're dealing with something that is acidic. So that is typical of an acidic solution. And we see things like black coffee, tomatoes, probably soda. I don't think it has it on there, but stomach acid, lemon juice, things of that nature. Hydrochloric acid, those are all acids that we're familiar with. And just lastly, I want to point out that when we look at a change in a unit of pH of just 1 unit. So notice when we go from, say, a pH of 4 to 5, if you look on the left-hand side of that sort of graphic, we see that the corresponding concentrations go from 10 to the minus 4 of hydronium concentration to 10 to the minus 5 when we go up to a pH of 5. So for every unit we move in pH, we're talking about an order of magnitude change in the hydronium ion concentration. And so that's where it ties back into what I was saying about the order of magnitude is what we're more interested in when we use a logarithmic scale. So let's see if we can go ahead and determine the pH of several different solutions. So if we go ahead and look at this, I have a pH. I want to determine the pH of a solution that is 10 to the minus 3 in the hydronium ion. So I just use my formula that we came up with the last time and plug it into minus log of 10 to the minus 3, and what we end up with is an answer of 3. Now, there's something that is a bit tricky about the sig figs on this. So what you'll notice is whatever we have for concentration, that 1.0 times 10 to the minus 3, that number has 2 sig figs. The pH will then have 2 sig figs after the decimal place. So we determine how many sig figs are in the pH by looking at how many sig figs are in the concentration. And so if it's 2 in the concentration of our solution of the hydronium ion, then it's going to be 2 after the decimal for the pH. Okay, so if it's a pH of 3, we should characterize it as acidic. Let's look at the next one. We just plug it in the formula, not too complicated. It has 2 sig figs. we end up with 9.00. So we had 2 sig figs in the 1.0. We should have 2 sig figs after the decimal place in the pH. pH at 9 we should expect, since it's greater than 7, is basic, and that's a basic solution. The next one, we have 3.4 times 10 to the minus 5, plug it into our equation, and again, so we end up with 4.47. Since we had 2 sig figs in the concentration, we have 2 sig figs in the pH after the decimal. This should be an acidic solution since it's less than 7. Next one, we plug in 5.77 times 10 to the minus 1. That's got 3 sig figs, so notice then we should expect to get 3 sig figs after the decimal place. So this is a solution that has a pH of 0.239. That is very low, and we should expect it to be acidic. Okay? Just pay attention to those sig figs. Those are a little bit tricky at first. All right, so what's the hydronium concentration if we are given the pH? So what formula should we be using for this? If that we look at that, this should be the first formula that we introduced, which was H3O plus equals 10 to the minus pH. So how do we treat the sig figs for the exponents in this case? Well, now we go ahead and if we look at 2 sig figs in the decimal of that argument for the pH, then now we have only 2 sig figs in the answer for the hydronium ion concentration. It's exactly the opposite of what we did just earlier. So going to that first one, we go to negative 7.0. This only has 1 sig fig after the decimal place for our argument there. That means we're only going to have 1 sig fig for the answer of the hydronium concentration. So it just becomes 1 times 10 to the minus 7 molar. For the next one, it's negative 4.0. Again, just 1 sig fig after the decimal, so we only end up with 1 sig fig in our answer for the hydronium concentration. It comes out to 10 to the minus 4 molar. For the next one, we have 10 to the negative 9.8. And again, we only have 2 sig figs. It's probably important to just calculate it exactly. And so we end up with 1.58 times 10 to the minus 10 molar. But then when we have to go down to the number of sig figs, it should be only 1 in that argument. So we get 2 times 10 to the minus 10 molar. For that last one, we have the hydronium concentration is equal to negative 0.87. Notice we have 2 numbers after the decimal place there. That means we are going to have 2 sig figs in our answer for the hydronium concentration. So I calculated exactly, and it gives me 1.35 times 10 to the minus 1 molar, or 0.135. And then when I go ahead and truncate it for the correct number of sig figs, it just ends up being 0.14. So this next one, what's the pH of a solution containing the strong acid HCl and results in a solution with a concentration of 3.5 times 10 to the minus 3 molar? So if we have the hydronium ion concentration or the H plus concentration, remember those two are equivalent, then what I just want to do to figure out the pH is minus log of just the argument here. So that is going to give me 2.46, and because I had 2 sig figs in the argument, I end up with 2 sig figs in the after the decimal, so I get 2.46, and that is E in this particular problem. This is what we just discussed, so I'll just go through that real slow. Okay. Let's see if we can calculate the pH of an aqueous ammonia solution that gives us a hydroxide concentration of 1.9 times 10 to the minus 3 molar, or 0.0019 molar, whatever we prefer. So again, we come back to this dissociation of water part that was in the last section that we covered, and we need to use the equation of Kw equals the hydronium times the hydroxide concentration, which equals 10 to the minus 14. And when we rearrange that for the hydronium ion concentration, which we'll need to figure out the pH, we end up with Kw over the hydroxide concentration. And so that's just 10 to the minus 14 over 1.9 times 10 to the minus 3. That leaves me with 5.3 times 10 to the minus 12 molar. So now I can plug that in, and I get a pH equals negative log of 5.3 times 10 to the minus 12 molar, 2 sig figs in there, So 2 sig figs in the pH after the decimal. So 11.28 would be the correct answer there. That is a basic solution. So let's look at acid rain. If we were doing a problem with acid rain, it says that is a matter of serious concern because most species of fish die in waters having a pH lower than 4.5 to 5. It says calculate the hydronium ion concentration in a lake that has a pH of 4.5. So this is when we're going to want to use that 10 to the minus pH. So we end up with 10 to the minus 4.5. And because we only have 1 sig fig after the decimal, we know we'll eventually have to truncate the concentration to only have 1 sig fig. So I calculated it out exactly. I get 3.16 times 10 to the minus 5 molar. And then when I truncate it, I end up with 3 times 10 to the minus 5 molar. If we're looking to determine the pH, one of the most common ways that we do that is we use acid-base indicators, as we have in several labs in the past semester, and I believe we have in this semester as well too. An acid-base indicator, as you might be familiar with, is just a substance that's going to change colors in a specific pH range. And so the indicator, when it becomes when it reacts and becomes in a more basic solution, that will result in the fact that the indicator loses its proton and you end up with a different color. So basically at some pH it's going to lose a proton or gain a proton, and that ends up changing the color of the complex that we have in solution, and that indicates some change in the pH. So this is a table that has several different indicators that we commonly use, and you can see that certain indicators are just going to be preferential to, say, low pHs. Like we look at that methyl violet, those are going to be good for when you want to determine a pH change that happens from anywhere from around one pH unit of 1. We can see that you have some like thymol blue that change in 2 ranges, right? So it can change around probably 1.7, also about 8.5 or so, or 8.7. It also changes. And so we can go to alizarin, well, let me see if I can say that, alizarin yellow. That changes around a pH of 11, so that helps us in the upper ranges when we're dealing with a very basic solution. And that's when we want to see some change. So we just use what's appropriate for whatever particular reaction we're doing, and that is something you go over in a lot more detail in something like analytical chemistry, and in here we'll probably have limited sort of overlap with making you guys decide what indicators are best, at least until chapter 15. We might go into it a little bit more. So what are strong acids and strong bases? Well, these things are considered strong acids or bases because they completely dissociate. So if you take a monoprotic acid, which we'll use quite a bit, it's always just characterized as HA. And the concentration of the hydronium ion that we get, and also the A minus that we get from the dissociation of that strong acid, is always going to be equal to the initial concentration of the HA, or the initial concentration of that strong acid you put into the solution. So if you put in a 3 molar, if you had a 3 molar solution of hydrochloric acid, a strong acid, you'd expect then to get a 3 molar concentration of hydronium and a 3 molar concentration of Cl minus, because it's going to disassociate completely. So this is the reaction, and notice that we have an arrow instead of an equilibrium arrow because this reaction is going to completion. We can treat it like we did reactions in the first semester of the class. So if I said calculate the pH of a 0.075 molar solution of nitric acid, HNO3, then we could just, since we know that it's also going to yield a concentration of 0.075 molar for the hydronium ion concentration, we can just plug that in and say pH equals minus log of 0.075, 2 sig figs there, 2 sig figs after the decimal, so we end up with 1.12. What about a solution of HCl that had 1.9 times 10 to the minus 4? Plug it in again. 2 sig figs in the number, 2 sig figs after the decimal place for the pH. So it's not as simple when we deal with diprotic or triprotic acids for the calculation of the pH. We can sort of see this if we looked at an example of sulfuric acid, which is a strong acid. And so when sulfuric acid does its first dissociation, it's going to create HSO4 minus and hydronium ion concentration. But the problem here is that even though H2SO4 completely dissociates, what ends up happening is the HSO4 minus that we're left with can still dissociate further, leaving us with a more acidic solution. So since it can undergo further dissociation with that polyprotic acid, it is more complicated to calculate the pH for this, and we'll take a look at it at a later time. So let's take a look at solutions in which we have a strong base. So strong bases also completely dissociate, and they yield the hydroxide ions. So if we look at a solution of, say, sodium hydroxide with a 0.025 molar solution, then how are we going to figure out what the pH of that solution is? Because this tells me how much hydroxide I'm going to have in solution. So you should be thinking back to that Kw equation. And if we rearrange that, we can go ahead and figure out what the hydronium concentration is from that. And in this particular problem, we do the 10 to the minus 14 over 0.025 and end up with a concentration of 4 times 10 to the minus 13 molar. Now that we have the hydronium ion concentration, it should be pretty straightforward to go ahead and calculate what the pH of the solution is, and we end up with 12.40. So let's look at a pH of a 4 molar KOH solution. So again, calculate the hydronium ion concentration. Once we do that, we can calculate what the pH is. And so those are pretty straightforward. Just remember, you can't use the hydronium or the hydroxide to directly calculate the pH. You need to find the hydronium ion concentration first. So what about in a solution of weak acids? How are we going to figure out what the pH is for these weak acids? The problem is that weak acids don't fully dissociate. And so they're governed by this equilibrium constant. We have some experience with that from the previous chapter, fortunately. So we would express the reaction for a dissociation of a weak acid as just HA plus water in equilibrium with just the hydronium ion concentration and A minus. So we can write a equilibrium constant for that, and for weak acids they have an equilibrium acid dissociation constant. So that Ka is another special another special designation we give to these equilibriums. So if you see a Ka, that means acid dissociation constant. And again, just I want to point out the fact that we're using those equilibrium arrows there because this is an equilibrium. So again, we're still looking at the with equilibrium constants. More often than not, we are often interested in the order of magnitude, and so we can do something like we did with pH, and we can define some pKa that for our acid dissociation equilibrium constant. And that pKa is very similar to what we define pH as, but this one is equal to the negative log of Ka, or the equilibrium constant for that acid dissociation. So pKa equals the minus log of Ka. When we have a smaller pKa, that's going to tend to mean we have a stronger acid. So we can look here on our chart here, and you can see hydrochloric. It's so large that it has a pKa that is negative in this case. And if we go to something like, say, ascorbic acid or vitamin C, it's got a pKa of 4.1, pretty reasonable. And so going to something like methanol, which is not very acidic at all, hardly dissociates at all, you end up with something that's as large as So let's see how we can figure out what the Ka is and the pK is if we have the molarity of HF here. So we have a 0.25 molar solution of HF, and we have a pH of 2.036. So what do we know in this particular problem? We have to sort of realize that when we're seeing 2.036 as the pH, that's an indication of what the hydronium ion concentration is. So we can leapfrog to, we know we've got that value at least, right? And so we can calculate what that hydronium ion concentration is quite readily. So if we have that, what else can we get? So we have HF reacting with water in equilibrium to form F minus and H3O plus. And this is starting to look a little bit like an ice type problem. So we set up our ice diagram. We know we started with 0.250 molar of HF, and we initially had 0 F minus and 0 H3O plus, right? Now the reaction is going to go to the right since we don't have anything on the right hand side. So we're going to lose some of that 0.250. We look at the stoichiometry. We're just going to have a minus X for a change for the HF. We're going to pick up an X on the F minus. We're going to pick up an X on the H3O plus. So now if we just sum up our two previous rows there, we end up with 0.250 minus X for HF and X's for F minus and hydronium ion. Now, we already know what the hydronium ion concentration is for the equilibrium. So we know X must be, in this case, that 9.20 times 10 to the minus 3. And so that also must be the X that we have for F minus. So if we know what X is, then we can just plug those values into the equilibrium constant that we've defined here as X squared over 0.25 minus X. And when I go ahead and I plug those values in there, I end up with a equilibrium constant that is 3.52 times 10 to the minus 4. If I want to determine what the pKa is, then I just do minus log of the Ka, which is going to give me negative log 3.52 times 10 to the minus 4 is going to give me 3.454 as our pH. Notice we had 3 sig figs on the concentrate or our value of Ka, so we're going to have 3 sig figs again in our value for the pKa. So it's just the same way as far as sig figs go as we had done with the pH. All right, so how can we use the known Ka value, this is probably a more common problem, to calculate the pH of a weak acid? So let's take a problem here where we have a 0.1 molar solution of HCN, and it has a Ka of 4.9 times 10 to the minus 10. It's at a temperature of 25 degrees Celsius, and we are to calculate what the pH is of this solution. So again, we go back to our ice diagram after we write our balanced equation, and we know we started with 0.1 and we had 0 of the products. So we end up with, according to the stoichiometry, we end up with a minus X on the HCN, an X on the CN minus, and an X on the hydronium ion concentration. Summing those two rows before us, we end up with 0.1 minus X for the hydrogen cyanide, and then we end up with the X on cyanide and an X on the hydronium ion concentration. Go ahead and plug those into our values for Ka, and I end up with X squared over 0.1 minus X. So this should be, in general, something that we go ahead and look at and go, oh, well, we need to rearrange it. A little bit of algebra here. And then once we've done that and we've gotten a form like this, this should look like the quadratic formula. So I plug that in. I get 7 times 10 to the minus 6 molar for the hydronium ion concentration. That tells me I can figure out what the cyanide concentration is from that. It should be the same. And if I wanted to, I could also figure out what the HCN concentration is from this particular problem. And so finding the pH, we just end up with a minus log of 7 times 10 to the minus 6. That yields 5.15. It's a slightly acidic solution. One note I do want to make is that the hydronium ion concentration present is pretty much solely from this HCN. We can consider it almost all from the HCN. The dissociation from water is very negligible. We discussed it earlier. It's something like 10 to the minus 7 molar. That's a very, very small number. So we're just going to consider that this is all we have to consider is the hydronium produced from the weak acid. Another thing to note is that the HCN started as 0.1, and if you want to go ahead and type in your calculator 0.10 minus 7 times 10 to the minus 6, you're going to find you basically end up with a 0.099999. You're going to end up with a lot of nines there because it's basically the same thing. It's still basically 0.10, and within sig figs it is still 0.10. And so that concentration barely changed. There was hardly any acid actually added from this weak acid. And that's where we're going to make a number of simplifications to many of our. Since we know that for a weak acid, this thing barely dissociates, we're going to proceed the same way through that problem. So you see this is the same ice diagram, same problem, everything else. But what we're going to do here is you see that we have one additional approximate sign at the very end there, and I've said that that last equation is x squared over 0.1, and I'm basically saying that that minus x is inconsequential. We just discussed the fact that if you subtracted it out, you'd still end up with 0.1. So it's pretty much inconsequential. So when you have those changes, a 0.1 minus x, or you could have like a 0.1 plus x in these problems sometimes. If the changes are incredibly small, then it's accurate to go ahead and just sort of ignore that change that we're looking at from the x. That also makes our problem a lot easier. So rearranging this just becomes x squared equals 0.1 times the Ka, and then I just have to do the square root of it. I end up with, hey, 7 times 10 to the minus 6 molar. So same thing that I ended up with in the last problem. So this obviously is a pretty darn good approximation. So it also simplifies our work a great deal. So that 7 times 10 to the minus 6 was really small, so it was accurate to use this approximation to ignore the change that we get from this dissociation and just leave it as 0.1. What we're going to say is basically for really weak acids, you're going to almost always end up with whatever initially you put in there is almost what you get at equilibrium, because not much is actually dissociating. And so we do need to make one check to make sure this is a valid assumption. And this is sort of this 5% rule. And so what we do is we basically take the value of x and we take it over the initial concentration of that HCN. And so in this particular case, if this inequality holds true, then what we're going to find is that the approximation is good. If it's false, we're going to say that the approximation is bad, and you have to go back to the quadratic formula. So let's check it for our particular problem. So we had 7 times 10 to the minus 6, and I do that over 0.1 molar, and then I have to multiply by 100. And what I end up with there is 0.007%. Still an incredibly small number, and that is much smaller than 5%. So the math checks out. This was a perfectly good assumption. And we're going to do that check on a number of problems to make sure that this assumption is good. Remember, if it's greater than 5%, then we have to go ahead and use the quadratic. So looking at this clicker question, it asks us to figure out what the pH of a 0.2 molar solution of acetylsalicylic acid is. And obviously acetylsalicylic acid is a long word, and the formula is obviously pretty big, as you can see there on the right hand side. So I took the liberty of just representing the acid as HA in this problem. So we have HA plus water reacting to give us A minus in hydronium ion concentration. If we're trying to figure this out, we probably want to set up an ice diagram. And so we know we started with 0.2 molar of the HA. We have 0 of the A minus in hydronium ion concentration. We should end up with a minus X for HA, X's for A minus in hydronium. And then when we sum them, we end up with a 0.2 minus X and XX. So setting up our Ka value, we know it's X squared over 0.2 minus X. I always like to make the approximation when I'm dealing with weak acids, and so I just basically swallow that minus x there, and it becomes x squared over 0.2. Remember, we have that Ka value up on the right-hand side as 3 times 10 to the minus 4. I'm just not plugging it in explicitly till I get to the end of the problem. And so we have x equals the square root of 0.2 times Ka. And so if we solve that, we end up with 7.75 times 10 to the minus 3 molar as the hydronium ion concentration. Plugging that in for our pH, we end up with a pH of 2.11. That's a good sign since we see C has that same value. But let's do one real quick check to make sure this is an okay approximation. So we end up with we take our value of X and then we divide it by the initial concentration of whatever the weak acid was. And so 0.2. Multiply that by 100, we end up with 3.9%. This is still smaller than 5%. We're getting closer to where this approximation wouldn't be valid, but it's still valid in this region. It gives us, a reasonable answer. So 2.11 is the correct answer. C is what we got. So percent dissociation in solutions of weak acids. So one thing that is true is weak acids tend to dissociate to a greater degree when the concentration is very small. We can sort of calculate what this percent dissociation is by looking at the HA that has dissociated divided by the initial concentration that we had, and we can multiply that by 100. We get a percent dissociation, and we can see, even looking at, say, this clicker question, we had 7.75 times 10 to the minus 3 molar. That was the amount that dissociated. We started with that 0.2 molar, and so multiplying it by 100, we end up with 3.88. And so that percent dissociation is basically what we're using to define whether our approximation is good. And so when we say the percent dissociation is greater than 5%, we're saying that it's not good enough to use that simplification we've been using. And so it's something we've already calculated, actually. And like I said, percent dissociation for all acids tends to increase as we go to lower concentrations. We can explain this using Le Chatelier's principle, and effectively, if we take basically A minus times the hydronium over HA, just looking at the acid dissociation equilibrium they have there, then we can see that because you have 2 species on the right and you only have 1 on the denominator, or sorry, 2 on the top on the numerator and 1 on the denominator, you end up with a 1 over V factor. And so as that volume starts to increase, if Ka is to stay the same, we have to favor the product. So the ratio on the left-hand side of the number of moles has to increase if the volume is also increasing, such that the Ka stays constant. So we get larger dissociation. In this case, you can see for the acetic acid in the chart to the right, or the graph to the right, we see a 4.2% dissociation at very low concentrations, but only something like 0.42% when we have a higher concentration. So that's it for this particular section, where we have one more section for chapter 14, and then we'll be finished with that. So